Welcome everybody, and welcome to this series of lectures on discrete mathematics and its applications. I'm going to be covering this textbook by Kenneth H. Rosen. I'm going to cover the 7th edition of this textbook. To understand mathematics, we must understand what makes up a correct mathematical argument, basically proofs. So let me write over here. Proofs make a valid mathematical argument. So, once we prove a mathematical statement, once we prove that it is true, we call it a theorem. So you start from a mathematical argument and you come up with theorems. A collection of theorems on a topic organizes what we know about this topic. And to learn a mathematical topic, a person needs to actively construct mathematical arguments on this topic and not just read exposition. So through this series, we will explain what makes up a correct mathematical argument and introduce tools to construct these arguments. So first, we start with propositional logic. The rules of logic give precise meanings to mathematical statements. These rules are used to distinguish between valid and invalid mathematical arguments. So, besides the importance of logic in understanding mathematical reasoning, logic has numerous applications to computer science. And this is what we're going to see through this propositional logic topic. These rules are used in design of computer circuits and construction of computer programs. It's also used in the verification of the correctness of programs and in many other ways. So propositional logic is a very useful and basic area that any computer scientist or any student in the computer discipline needs to master. So we'll start with the definition. A proposition, according to a definition, is a declarative sentence. It's a sentence that declares a fact, and this fact can be either true or false. Here's an example. Look at the 4 statements in example number 1. Statement number 1 says, Washington, D.C. is the capital of the United States of America. Statement number 2 says, Toronto is the capital of Canada. Statement number 3 says, 1 plus 1 equals 2. And statement number 4 says, 2 plus 2 equals 3. Notice that these are declarative sentences. Okay? These 4 statements, they fall under the definition that we have mentioned over here. And hence, they are propositions. And these propositions are stating facts. And these facts can be either true or false. You can instantly notice that proposition number 1 and proposition number 3 are true, whereas proposition number 2 and proposition number 4 are false. Now, in order to make the definition of proposition more clear, look at example 2. In example 2, sentences 1 and 2 are not propositions. Look at sentence 1, which says, what time is it? And sentence 2, read this carefully. They are not propositions because they are not declarative sentences. If you look at sentence number 3 and 4, they are not propositions as well because they are neither true nor false. So these two are not declarative sentences, and these two can neither be true or false. I want you to note that we use letters to denote propositional variables or statement variables. That is, variables that represent propositions are just letters and used to denote numerical, just like they denote numerical values. So the conventional letters to use proposition variables are, for example, P, or maybe Q, or R, or S. So if you go to example number 1, we can say that the first statement can be, we can use a declarative variable P to represent the first statement, propositional variable, sorry, P to represent the first statement. We can use the proposition variable Q to represent the fourth statement, and so on. Also, the truth value of proposition is true, and if a proposition is true, we denote it by the capital letter T, and if the proposition, another proposition Q, is false, then we denote it by the letter F. So the truth value of true is denoted by letter T, and the truth value of false is denoted by the letter F. The area of logic that deals with propositions is called the propositional calculus, or propositional logic. It was first developed systematically by the Greek philosopher Aristotle more than 2,300 years ago. Now, one may ask, are there any methods for producing new propositions from those that we already have? The answer is yes. These methods were discussed by the English mathematician George Boole in 1854 in his book, The Laws of Thought. Many mathematical statements are constructed by combining one or more propositions, and new propositions called compound propositions are formed from existing propositions using logical operators. And now we're going to look at some of these logical operators that will help us to create compound propositions. The first one is the negation operator. Let me read through the definition. Let P be a proposition. The negation of P, denoted by not P, this is pronounced as not. The symbol here is pronounced as not. Okay. So the negation of P, denoted by not P, is the statement, it is not the case that P. Let us look at this example here. Example number 3. The example says, find the negation of the proposition Michael's PC runs Linux. And the negation is, according to the definition, let me put the definition into perspective as well. According to the definition, let's say if this is denoted by proposition P, then the negation of P is represented by the sentence. Let's apply the definition. It is not the case that Michael's PC runs Linux. Now, this negation can also be written in a more simple way, or expressed simply by saying, or we can say not P can be rewritten as Michael's PC does not run Linux. By the way, you have to specify. Okay, so now in simple statements like these, you may rewrite your negation statements in a more shorter way, depending on the level of command you have on the English language or any language you're using. But let's say in more complex statements, when ambiguity or confusion arises, it's the best strategy to take is just apply the definition as is, which is affixing the statement with with it is not the case, and you will get the negation of that statement. Let's take another example to understand the negation completely. Here is example number 4. which says find the negation of the proposition Vandana's smartphone has at least 32 gigabytes of memory, and express it in English, in simple English. So the negation of that is, let's apply the definition directly first. It is not the case that Vandana or Vandana's smartphone has at least 32 gigabytes of memory. This negation can also be expressed as Vandana's smartphone does not have at least 32 gigabytes of memory. Now, and even one can also make it more simple in the English language by saying Vandana's smartphone has less than 32 gigabytes of memory. Now notice that all three statements are logically equivalent, and all three statements are the negation of the first statement that is given in example number 4 over here. So let's say you don't have the strong command of the English language. So the best way to negate a proposition is by applying the definition directly and affixing it is not the case that, and affix this to the proposition that you have. Now let's look at the truth table for the negation of proposition P, and here it is. This table shows a row for each of the two possible truth values of the proposition P. Each row also shows the truth value of the proposition not P, or the negation of P. The negation of a proposition can also be considered the result of the operation of the negation operator, which is shown over here. The negation operator constructs a new proposition from a single existing proposition. So keep in mind that if P is a proposition, then not P is a new proposition. With negation on the side, now let's look at other logical operators that are used to form new propositions from two or more existing propositions. These logical operators are called connectives. So the first logical operator, or connective logical operator, we're going to see is the conjunction. Let me read out the definition. Let P and Q be propositions. The conjunction of P and Q, denoted by P and Q using this symbol, is the proposition P and Q. The conjunction P and Q is true when both P and Q are true and is false otherwise. Now, this part of the definition is very important because it defines the truth table that we see here, that denoted by table 2. This table displays the truth table of P and Q. This table has a row for each of the four possibilities or possible combinations of the truth values of P and Q. The four rows here, the rows that you see, correspond to the pairs of the truth values true and true, true and false, false and true, false and false. Now, according to the definition, if we have a pair of true and true, then the conjunction of this pair is going to be true according to the definition here. and otherwise the outcome of this pair is going to be false. Note that in logic, the word but sometimes is used instead of and in a conjunction. For example, the statement "the sun is shining but it is rising" is another way of saying the sun is shining and it is rising. In natural language, there is a subtle difference in meaning between and but. But will not be we will not be concerned with the nuisance here, and hence we're going to concentrate, or we're going to always come back to the definition of the conjunction. So let's look at an example. Example 5 says, find the conjunction of the propositions P and Q, where P is the proposition Rebecca's PC has more than 16 gigabytes free hard disk space, and Q is the proposition the processor in Rebecca's PC runs faster than 1 gigahertz. The answer for this is, well, basically we want to find the conjunction. So the conjunction of these propositions, we'll write it as P and Q, can be written as Rebecca's PC has more than 16 gigabytes free hard disk space, and this is the connecting operator, the processor in Rebecca's PC, or is it in Rebecca's PC, runs faster than 1 gigahertz. Now, I need some more space to continue with the discussion of this example, so I'll move the tables a little bit to the end of the screen. Now, this conjunction can be expressed more simply as Rebecca's PC has more than 16 GB free hard disk space, and its processor runs faster than 1 gigahertz. Now, for this conjunction to be true, both conditions given must be true, and it is false otherwise if one of the two conditions are false. So, as you can see, as I said earlier, if you don't have a good command of the English language or the language that you are using, then just apply the definition as is, which is write the first proposition and then connect it with the second proposition with an and word over here, and you'll be done. Another connective operator is the disjunction operator. And before I go to the definition, let me just move these artifacts a little bit away because I need that space for the discussion and for writing. So now, according to the based on the definition, the disjunction, let P and Q be propositions. The disjunction of P and Q, also denoted by this symbol over here, is the proposition P or Q. And keep in mind that in the disjunction, the disjunction of two propositions is false when both P and Q are false and true otherwise. And this is depicted in this table here. As you can see, the four pairs are there in table 3. You've got the true pair, the true false pair, false true pair, and the false pair. And based on the definition, it is false only when both of them are false. Otherwise, the composition of this compound proposition, the value of the value of the compound proposition is going to be true, as we've seen. Now, the use of the connective or in a disjunction corresponds to one of the two ways the word or is used in the English language. And basically what we mean over here is that the or that we represent, or that we want to highlight over here, is the inclusive or. So, in the inclusive or, the operator that we are discussing over here, a disjunction is true when at least one of the two propositions is true. For instance, the inclusive or is being used in this statement: students who have taken calculus or, so look at this or, computer science can take this class. Now here we mean that students who have taken both calculus and computer science can take the class, as well as the students who have taken only one of the two subjects. Now, if, on the other hand, we want to use the exclusive or, we may say, let me write the exclusive or. So for the exclusive or, we may say students who have taken calculus or computer science, but not both, can enroll in this class. So now, in the second statement, we mean that students who have taken both calculus and a computer science course cannot take the class. Only those who have taken exactly one of the two courses can take the class. Now, in the same way, when we go to a restaurant and in the menu we read soup or salad comes with an entree, the restaurant almost always means that customers can have either soup or salad, but not both. So this is an exclusive rather than an inclusive or. So disjunction is considered to be an inclusive or, and a third operator, which is the exclusive or we will see that, we'll take it later on, is called the exclusive or, is going to handle the other cases. So let's look at this example. Example 6 is based on example 5. So example 6 says, what is the disjunction of the propositions P and Q, where P and Q are the propositions, as in example 5. I've just put the example 5 in front of us here so that we know what we are up against. And the disjunction here we can write P or Q is the proposition Rebecca's PC has at least 16 gigabytes free hard disk space. Or, here's the connective operator, the processor in because PC runs faster than 1 gigahertz. So as you can see, just like in the previous example, we can rewrite this this statement, or the disjunction statement, in a much simpler way. But of course, that is just left for your skills in the command of the English language. But as far as propositional logic is concerned, as far as mathematics is concerned, whatever we have written over here is sufficient and enough to describe the compound proposition of P or Q. It is worth pointing out that when the exclusive OR is used to connect the propositions P and Q, the propositions P or Q, but not both, is obtained. Let me clear up the place over here so that I can explain what I mean. I'll take this out of the other way. Yeah. So when we are saying, when we use the exclusive OR, we say P exclusive OR. I'm going to name it as P exclusive OR Q. Then basically what we mean is P or Q, but not both. Now this proposition is true when P is true, okay, and Q is false. Or it's also true when P is false. So when P is false and Q is true. And this whole proposition is false. Oops. This whole proposition is false when both P and Q are false. And this is what is conveyed by the truth table over here. I'll put it on the right, as you can see. And the definition also says the exact same thing. Next, let's look at the conditional statement. Let me read out the definition first. Let P and Q be propositions. The conditional statement P implies Q, this is how we denote it, is the proposition if P then Q. Now there are some things to be noted here. The conditional statement P implies Q is false when P is true and Q is false, and true otherwise. And another thing is that the first statement, in the conditional statement, P is called the hypothesis and Q is called the conclusion. Now, keep in mind that for the statement P implies Q, it's called a conditional statement because P implies Q asserts that Q is true. This is going to be true on the condition that P holds. A conditional statement of this kind is also called an implication, and throughout these video series, I'm going to say P implies Q for short to indicate the implication statement. Also note that this statement P implies Q is true when both P and Q are true and when P is false. So if P is true and Q is true, then the whole statement true implies true is going to be true. And the same way, if both are false, if we have false implies false, then the whole statement is going to be also true, which is indicated in the table in front of you here. Now, because the conditional statement plays such an essential role in mathematics or mathematical reasoning, a variety of terminology is used to express P implies Q. We are going to encounter most of them in the exercises and so on, but I'll just mention, I'll just list a few in front of you. So in regular language, we can encounter expressions such as if P then Q, if PQ, or if P is sufficient for Q, Q if P, and so on. A useful way to understand the truth value of a conditional statement is to think of an obligation or a contract. For example, let's say a politician usually pledges that with the following statement: if I am elected, then I will lower taxes. This is a conditional statement. Now, if the politician is elected, so let's say if this is true, if the politician is elected, voters would expect that this politician will lower taxes. Okay? Furthermore, if the politician is not elected, so if this is false, then the voters will not have any expectation of the taxes and the reduction of taxes, for example. Although the person may have sufficient influence to cause those in power to lower taxes, but for the overall, still, the people will not expect for taxes to be lowered. Now, it is only when the politician is elected but does not lower taxes, so the politician is elected but does not lower taxes, only when this happens, this case happens, okay, only then the common people or the people who elected the politician will feel that they are cheated. And this is the only this is the only case where the whole outcome of the conditional statement is going to be false, and that is exactly what is depicted in this table, the truth table of the conditional statement in front of you. Now, the same reasoning can be done for the next statement here. If you get 100% on the final, then you will get an A. And the only way this is going to be false, if somebody gets 100% but they don't get an A, hence they are going to be very angry and might go and talk with the instructor and fight for the grades based on the promise that was given over here. So let's do a simple exercise in example 7, using example 7. Example 7 says, let P be the statement Maria learns discrete mathematics, and Q is the statement Maria will find a job. And we want to express the statement P implies Q as a statement in English. So first we're going to take the direct method. So P implies Q can be written as if Maria learns discrete math, then she will be, oh, not be, she will find a good job. Now, as I mentioned earlier, that you can express this in several different ways, as you've seen over here. You can express the conditional statement in several different ways. Another way to express P implies Q can be written as follows. P implies Q can also be written as for Maria to get a job, it is sufficient for her to learn discrete math. And of course, you can, as an exercise, you can try to express the same statement in several different ways, basing your expressions on one of the expressions that is shown over here. Another thing to mention, the if-then construction used in many programming languages is different from that used in logic. Most programming languages contain statements such as if P, then S. So for example, let me write it over here. In many programming languages, we use the construct that says if some condition P, then some statement S. And P is a proposition, and S is the programming segment. When execution of a program encounters such a statement, S is executed only if P is true. And this is a little bit different than the implication or the conditional statement or the implication statement in logic. So next we'll look at the converse, contrapositive, and the inverse. If you look over here, I'll read through the definitions. We can form new conditional statements starting with the conditional statement P implies Q as follows. The converse is Q implies P. The contrapositive is not Q implies not P. And the inverse is not P implies not Q. Now, please, if you look at it, you can note that the contrapositive is false only when not P is false and not Q is true. So look at the contrapositive, not Q implies not P. This whole thing is false when what? When not P is false and not Q is true. This means that from here we get that P is true, and from here we get that Q is false. And this means that basically this behavior is the exact behavior that we see in the conditional statement. So this is one way of giving the reasoning behind the logical equivalence of these two statements, the conditional statement and the contrapositive statement. Now, after a while, just in a few moments, we're going to use a different way called the truth table method that we will cover over here. That will also give us an indication, or give us another way to prove that these two statements, the conditional statement and the contrapositive statement, are logically equivalent. And through that, we are also going to see that the conditional statement is not logically equivalent to the converse, nor it is logically equivalent to the inverse of the statement. Another thing I'd like to mention is that when two compound propositions always have the same truth value, we call them equivalent. And that's what I was talking about a while ago, about these two statements, the conditional statement and the contrapositive statement. The converse and the inverse of a conditional statement are also equivalent. So we've got this and this are also logically equivalent to each other, but they're not equivalent to the conditional statement. You may take a note that one of the most common logic errors is to assume that the converse or the inverse of a conditional statement is equivalent to the conditional statement, which is not true. If you just be a little bit patient, when we reach the truth table, it's going to be more easier to grasp and understand. So, just to let these concepts sink in, let's take a simple example. Here's an example. It says, what are the contrapositive, the converse, and the inverse of the conditional statement? The home team wins whenever it is raining. So let's identify P and Q. First of all, notice that this statement is written in the form of Q whenever P. So this is one way to express the conditional statement, and hence this whole statement is basically expressing P implies Q. So in this case we have this is defined, it is identified as P, and this is identified as Q. So now let's write the original statement. The original statement can be written as if it is raining, then the home team wins. So this is the original statement. Okay. Let me put this back as it was. Yes, there you go. So the contrapositive, okay, can be, which is not Q implies not P, can be written as follows. If the home team does not win, then it is not raining. And the converse? The converse would be if the home team wins, then it is raining. And in the same fashion, you can think of the inverse. How can you write the way we write the inverse is as follows. The inverse, if it is not raining, then the home team does not win. Now you've noticed that only the contrapositive is equivalent to the original statement. Only this statement is original to the, or logically equivalent to the original statement. The others are not logically equivalent. The next operator we're going to look at is the bidirectional operator. And according to the definition, the bidirectional statement, written as this, is the proposition P if and only if Q. The bidirectional statement is true when P and Q have the same truth values, keep that in mind, and false otherwise. So basically, if you want to write the bidirectional statement using the previous operator's terminology, P if and only if Q is logically equivalent to P implies Q and Q implies P. Now notice I have been using this symbol, okay. I've been abusing this notation. As we go on in this series, I'll be using this symbol to indicate the equivalence of two logical expressions. So I would like to apologize if that creates confusion, but as we go on through the series, you will also get used to this slight abuse of notation. There are some other common ways to express P if and only if Q in the English language, and here are three examples. P is necessary and sufficient for Q, if P then Q, and conversely, and P if and only if Q. So you may find these expressions used in different contexts in different textbooks, but they all are equivalent, or they're all different ways to express the same condition, the bidirectional statements when working with logic. Furthermore, based on the definition over here, we can see that this is the truth table, and as you can, if the two pairs of P and Q are true, or the two pairs are false, then the bidirectional statement, the compound statement, is true. Otherwise, it is false. And this is exactly in accordance with the definition of the bidirectional operator. Well, now that we've gotten acquainted with four more important, quite important logical connectives, namely the conjunction, the disjunction, the conditional statement, and the bidirectional statement, as well as the negation, we can use these connectives to build up complicated compound propositions involving any number of propositional variables. We can use truth table to determine the truth values of these compound propositions. I'll demonstrate that using this example. The example says, construct the truth table of the compound proposition P or not Q implies P and Q. So I'm going to build the truth table for these and I'm going to take the individual propositions and assign them a column. So in this column, I'm going to assign, dedicate it for the proposition P. The next column, I'm going to dedicate it for proposition Q. And I'm going to assign them truth values. So for P, I'm going to assign values true, true, false, and false. And for Q, it's true, false, true, and false. Now the reason I'm putting it in this pattern, in this specific pattern, is that I want to cover all the different combination of pairs between the values, the truth values of P and Q. So true, 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 false, false, true, false, false covers all the different combinations of these truth values. Now, if you look at this compound proposition, you'll see that not Q is the truth values of not Q needs to be known. So I'm going to dedicate another column for the not Q over here. Now, once not Q is known, I can then compose the truth values for this part of the left part of the compound proposition. So I'm going to dedicate a column for P or not Q and another column for P or Q. And then once I've determined the truth values for all of these, I'm going to dedicate the last column for the actual compound statement for which we want to find the truth values. So now for the not Q, the truth values is simple. For truth, it's the not Q is going to be false. For false, the not is going to be true. True, not Q is going to be false, and if Q is false, the not Q is going to be true. Now, just for your reference, I have let me just pull the truth tables into the view for the conjunction, the disjunction, and the conditional statement. Okay, this is for demonstration purposes only. If you are a student and preparing for the exam, I would advise that you memorize these the truth tables so that you can solve the questions of the exam, unless you're allowed to take a formula sheet with you in the exam, but in that case that's another story. So let's continue with this example. So now I need to calculate the truth values for P or not Q. So I need to look for the truth values between this column and this column here. With the or, let's go back to the disjunction table, and in the disjunction table, notice that all the values are true except when both of them are false. So let's look at this. True or false is true, true or true is true, false or false is false. This falls under the bottom row, and false or true is true in this case. And then we look at P and Q. Going back to the conjunction truth table, we'll see that this is always false except when both of them are true. So we'll look at P and Q over here. True and true is true, and everything else is false. So basically we're just like copying this table into this this row over here from this table into this. Now that we have everything computed, we can compute the truth value of the final propositional compound statement or compound proposition. In this case, we're going to just do the calculate using the conditional statement truth table. We'll calculate the truth value of the final statement, and notice over here that only when the second proposition is false, then the whole proposition, the compound proposition, is false. So in this case it's going to be true. Over here it's going to be false. False and false, false implies false, gives us true. And if you look back, true implies false, it gives, true implies false, it gives us false. And then, and basically this final column gives us the truth value of the truth table for the compound statement given in this example. Now you must have noticed that while building this truth table, I applied some operators before the others. You must have noticed that I have calculated the not Q column here before I calculated the P or not Q or any others. The reason for that is that in propositional logic, you need to observe the precedence of logical operators, and the precedence of logical operators is given here on the top right corner in table 8. And as you can see, the not operator has the highest precedence, number 1 in this table, and that's why if you get a compound proposition, then the first thing you need to calculate in order to find the truth value of the whole statement is you have to apply the not operator first, and then you follow the precedence depending on the precedence given for the operators in this table. Another general rule of precedence is that the conjunction operator takes precedence over the disjunction operator. So if we have a compound statement like so, P or Q, P and Q or R, this actually means that P and Q, then we apply the or operator. And this is exactly consistent with the precedence rule that we see in the table of precedence. So if you are getting confused, the best way to go about it is to parenthesize your compound statement based on the precedence, the operator precedence table shown earlier. So now that we know how to use the truth table to check the equivalency of different compound statements, let's come back to the converse, contrapositive, and the inverse statements and see how to prove the equivalence or non-equivalence between them. So first I'm going to just erase this to clear up some space. Then I'm going to construct a truth table. I need to use the pen. Construct a truth table, and in this truth table I'm going to have a column for P, another column for Q, and with truth values truth, truth, false, and false, and then true, false, true, and false. Now, just not to get confused, I'm going to just separate two rows at a time. Now, first, I'm going to we want to see that the conditional statement, and we want to compare the conditional statement with the contrapositive. Not Q implies not P, and I want to compare it with the converse. Q implies P, and the inverse, not P implies not Q. So now, in the same way, just so that to compute these, I need to compute the not Q and the not P. So I am going to extend this a little bit to the right. Whoops, that's too much. Let me take it one step further. Okay, and I'm going to put not P over here and not Q. Yep, not Q. There you go. So now not P is going to carry the values. Whoops, where did that go? Yeah, it's going to carry the value false and false, true and true, and not Q is going to carry the value false, true, false, true. You can compare that with the with the original columns. And let me just position it so that we can see everything. That's good. Let me pull this a little bit down. Okay, good. Now, so no, I need to put this back so we can see the tables on the top. So P implies Q. Basically, I'm going to copy this whole column as it is. So you got 2 TF and then T, or truth and false, then true and true. Now, not Q implies not P, so we're going to use these two columns to compose the column for not Q implies not P. So not Q, false, and then not P implies not P, false. False implies false is true. Come over here, not Q, true, or not true. Not Q is true, implies not P is false, so true implies false. True implies false is false, according to the table. False implies true. False implies true is true, and then true implies true is true according to this. And there you go. Here's the column for not Q implies not P. Let's do Q implies P. So Q implies P, true implies true is true, and then oops, moved again. And then false implies true is also true, and then true implies false is false, and then false implies false is true. All I'm doing is I'm looking at these values over here, and I'm using this table as a reference, and then from this table I'm just calculating the values over here. Now you can do this with me. Let's do it together. Not P implies not Q. So not P implies not Q. So false implies false is true. False implies true is also true. True implies false according to this row here is false, and true implies true according to the first row is true. And now you must have noticed that this column and this column are the same, and hence we say that the conditional statement and the contrapositive statements are logically equivalent. And you can notice that, let me use a different color, say green. You would notice that this and this column are the same, and that's why we earlier I mentioned that the converse and the inverse are logically equivalent. And this table, the truth table, shows that that the conditional statement is not equivalent to the inverse. Neither it's equivalent to the converse statement. Now, the last point I'd like to mention is that computers represent information using bits. A bit is just a symbol with two possible values, 0 and 1, as shown in this table over here. A bit can be used to represent a truth value because there are two truth values, true and false, so we can have a mapping between the two truth values and the two values of the bit that we can have. As it is customarily done, the 1 is equivalent or represents true in digital logic or in computers, and 0 is represents false or is mapped to false. And as with propositional logic, computer bit operations correspond to the logical connectives. By replacing the true by 1 and false by 0 in the table, we get the bit operations, and as you can see in table 9 here. And basically there's a one-to-one correspondence to every operation that can be done between in bits or in logic using true and false values. So based on that, we can have a definition of a bit string, which is a sequence of 0 or more bits. The length of this string is the number of bits in the bit string. An example of a bit string is what you see over here, a sequence of zeros and ones. And we can apply pairwise operations on them. Either we called it bitwise or bitwise and bitwise exclusive OR. So let's look at this in action by considering example 13. So what I'm going to do is in example 13, it's asking me to calculate bitwise OR, bitwise and, bitwise exclusive OR between the two strings. This is the first string, the second string. So what I'm going to do is I'm going to just write them in pairs of 4-bit strings just for aesthetic purposes and to avoid errors. So we got 0, 0, this is a 0 and 0, 1, and we've got 1, 1, 0, 1. So let's say we want to do a bitwise OR. So 0 or 1 is 1, and think of it as false or true is true. Okay, so 1 or 0 is also 1, 1 and 1 is 1 or 1 is 1, 0 or 1 is 1. Remember that OR gives us a false if we have both values to be false. So we will get a 0 only if both values are 0. So let's continue. 1 or 1 is 1, 1 or 0 is 1, 0 or 0 is 0. There you go. It's the only pair that gives us a 0 for the OR operator. The 1 or 0 is 1. The same way here, 1 or 1 is 1, 0 or 1 is 1. So this is how we calculate the bitwise OR of two bit strings. Now let's do the same thing. Let's calculate the bitwise AND for this. And remember, in the AND operator or the conjunction operator, you will get one only if both of them are 1. Otherwise, you'll get a 0. So 1 and 0. Oh, sorry, 0 and 1 is 0. 0 and 1 is 0. 1 and 0 is 0. 1 and 1 is the only pair that's going to give me 1. Otherwise, this is the next one is going to be 0. 1 and 1 is going to give me 1. 1 and 0 is 0. 0 is 0. 0 and 0 is 0. 1 and 0 is 0. In the same way, 1 and 1 is going to give me 1. 0 and 1 is going to give me 0. The same way we can do the bitwise exclusive OR. And if you remember the bitwise exclusive OR, 0 exclusive OR 1 is going to give me 1. 1 exclusive OR 0 is going to give me 1. and then 1 exclusive or 1 is going to give me 0. If you do not recall, if the pair are different, we're going to get 1. If the pair are the same, we're going to get 0. So 0 XOR 1 is 1, 1 XOR 1 is 0, and then this one, 1 XOR 0 is 1, 0 XOR 0 is 0, and 1 XOR 0 is 1, 1 XOR 1 is 0, 0 XOR 1 is 1, and that's how you do the bitwise XORing between of 2 bit strings. With this, we come to the end of section 1.1. We have covered the basic building blocks of propositional logic. Thank you for following this series, and I hope to see you in the next recording.